speak today we will speak about expressions for local time for Gaussian processes. What does it mean? We already discussed with you following objects. If we have some random field which is defined on the domain D Rn, and we consider some point y0 from Rn, where site takes its values, and say that such a formal expression, integral over d, delta y0 from psi of u du was named by the local time of psi at the point y0, and we already have seen some useful properties of this object. For example, we checked that if properly defined with appropriate limit procedure, then this object as a function of y0 became to be density of the visitation measure of our random field psi. Also, on the first lecture, we discussed that existence of non-trivial local time, which is not equal to 0, almost surely, means that in particular our random field visits this point y0. And we discussed different examples where to know whether a random field visits a point or not is important problem. Due to all these reasons, it is useful to understand how we can express local time when it exists, and how we can work with it as with the random variables. What is the relationship of this value to the value of initial process psi? How one can organize this value from the initial values of psi? There is one class of random fields where we can have some answers on these questions. So we can think about the expression of local time for Gaussian random fields. So today we will discuss expression of the local time for Gaussian random fields. First of all, let me recall you some definition from the previous some definition from the previous lecture, which is useful today. Namely, I will consider the random vector theta, which consists of d coordinates and this random vector eta is called Gaussian. Is called Gaussian if its characteristic function, namely expectation of the exponent imaginary unit multiplied by the scalar product of some vector from Rd, our random vector eta, can be expressed as follows. It is equal to exponent E scalar product lambda A minus 1/2. Here is some quadratic form of the matrix sigma applied to the vector lambda. A now is an expectation of our random vector eta, and sigma is its covariance matrix. It is covariance eta. And trivially it is symmetric and non-negative matrix. We already know that in some cases, namely when sigma is strongly positive matrix, this random vector has a density. In case when A is 0 and sigma is identity matrix, we will say that eta has standard normal distribution. So in case when A is equal to 0 and sigma is identity matrix, we will say that eta is standard function vector. And denote its distribution as usual normal distribution with parameters 0 and identity. How one can speak about Gaussian vectors and Gaussian random fields? I recall you again the definition from the previous lecture that the field is Gaussian if we take any finite number, its values and its coordinates, and altogether they organize Gaussian vector for arbitrary value of parameters, for arbitrary choice of coordinates. This is the definition of Gaussian vector field, and today we will work with it. So the question is, in which terms it's better to speak about Gaussian vector fields and functionals for it? Maybe it is useful to have something like standard Gaussian vector, Gaussian random field, and express another Gaussian random vectors and fields as a functional from standard one. So let's proceed in this direction. To do this, let me recall that we already have standard vectors. So if we have dv, we have here standard Gaussian vector eta. I will use notation as we already introduced, which we already introduced. And then one can think about this object as a source of another random vectors. For example, how one can get another random vectors. Suppose that I want to have Gaussian random vector with in the same space, but with the non-trivial union A and some covariance matrix sigma. How I can get such distribution from this? It's easy because you remember we already know that sigma is a covariance matrix. So one can easily check that it is symmetric or self-adjoint. We discussed a real space, so it does not matter to say symmetric or self-adjoint for matrix. And it is greater or equal than 0. So from linear algebra, we know that there exists square root of sigma. Let us denote it by S. This is square root of sigma. And this is again symmetric matrix, which is non-negative, and such that S multiplied S is equal to sigma. So S is symmetric, S is non-negative, and S square is equal to sigma. Now, using S and A, we can construct vector with such distribution from this. How will we do this? Let us consider a random vector zeta, which is equal to A plus S of theta. It is trivial that it is again Gaussian vector. You can check this. Also, let us check its parameters. Evidently, expectation of zeta is equal to A, and covariance of zeta will be equal S star S, and it is equal to sigma. It is equal S star S and it is equal to sigma. From this point of view, one can see that we can get arbitrary Gaussian vector from the standard one. It means that we can make the same attempt when consider random fields or random processes. Roughly speaking, when consider a family of jointly Gaussian random variables, much more bigger than finite one. Maybe to do this, we need to enlarge our space. It is not natural to expect, for example, that we can express the process of Brownian motion using only finite dimensional standard Gaussian vector. So first, what we will do today, we will enlarge this construction of the Gaussian standard random vector. What I will do? I will try to substitute our space RT by the space H, which will be a separate real separate Hilbert space. So I already have a much more bigger space than this one. Now I want to have analog of the standard Gaussian vector here. How one can proceed? You remember that standard Gaussian vector was expressed in terms of its coordinates. Yeah. By the way, the coordinates of standard Gaussian vector were uncorrelated and jointly Gaussian, so one can check that they are independent. So maybe we can proceed in the same way. Let us consider now some basis here. It exists because the space is separate, and try to organize infinitely long chain of coordinates, which will be independent standard Gaussian values. Let us try to Excuse me? Oh, now it is clear. Okay, let's try to do this. So I will take as a basis image. Let n is greater or equal than 1 is orthonormal. Orthonormal basis in the space H. As I said, it exists due to the fact that our space H is separate. Now, let us try to organize infinitely dimensional vector. So I will take eta n. It will be a sequence. IID sequence independent identity distributed random variable. And every eta, I will let it for have a standard normal one-dimensional distribution. So what I'm doing, I just take the sequence of coordinates for hypothetical Gaussian standard random vector in our space H. Now, let's make next step. So one can try to organize standard Gaussian vector in the space H as follows. Eta, I will not write arrows because we write arrows when we have finite dimensional vector and stop to write it again when we have an infinite dimensional space. So we will try to see the following sum. From n equal 1 to infinity, here is eta n n. This is coordinate eta n element of the basis. Formally, it looks very similar, like in the space RD, because in the space RD, if we take canonical basis like this vector is a vector which consists of zeros, and here 1 is again zeros, and that's all. Then one can check that our vector eta was a finite sum from k equal 1 d eta k ek. So you see these two expressions are almost the same. Only one difference is this infinity here. But this difference is crucial. Namely, if you want to check that our formal series give us element in Hilbert space, we have to check some relationship. We already know, at least from Fourier series theory, that we must have Parseval identity. Namely, if we take Hilbert norm of our vector, our element, it must be equal to sum from n equal 1 to infinity. Here is eta n squared. Yes, such relation must hold. Moreover, if it holds, we know that it must be less than infinity with probability 1. It must be less than infinity with probability 1. But you can check that this series diverge with probability 1. It is easy to check because eta n are IID, the identical distributed standard random variables, standard normal random variables. So one can easily check using Borel-Cantelli lemma that general member, general summand in our series does not converge to 0 with probability 1. It means that this relation doesn't hold. And for us, this is very bad news because we understand that this formal sum does not converge and it does not define any element in our Hilbert space. There are no any element in our Hilbert space which can be expressed with such identically distributed, independent, standard normal coordinates. But nevertheless, here we have some small and thin rod phase, because instead of considering such an element, one can try to do the following thing. Let us take arbitrary element H from our space. Then this element H for sure has an expression as an infinite sum from n equal 1 to infinity alpha n en. Here alpha n are coordinates of the vector H, of the element H, and now we of course have Parseval equality. So we have this equality that norm of H squared is equal to n to the sum from n to 50 alpha n squared, and of course if the sum is less than infinity. Now one can do the following. We have not such an element. It does not exist. So I will not write here equality, but something like this. It does not exist. But one can try to consider scalar product of H and eta. Of H and eta. What it will be? What it will be? I just recall you that when we consider scalar product of two different elements in Hilbert space, then the scalar product H eta. Excuse me? Can I continue?
Yes.
Okay. So this will be equal to the following. Sum from n equal to infinity. And here products of corresponding coordinates. And now we have a good news. Because of the conditions on the alpha, I recall that sum of alpha squares is finite. One can check that this series converge in square mean almost surely and so on. For example, I will check that it converges in the square. Let us do this. Let us denote by S and its partial sum. This is the sum from K equal 1 to N alpha K eta K. Then one can discuss expectation of S M minus S M in square. Considering this expression, I will think that M is real. Then it is equal to, due to the fact I just recall you that eta n are IID standard random variables. So they are independent, they have zero mean and variance equal to 1. Due to this, one can easily check that this expression is equal to sum from k equal n plus 1 to m alpha k squared. It's easy to check this. And when we check it, it follows that. It follows that it goes to 0 when n and m tends to 0. Because the series of alpha k squared converge. It means that this sequence is a Cauchy sequence in the space of square integrated random variables, and it means that the value which we discussed, namely h eta equal to sum from n equal 1 to 50. Here is alpha n, eta n, converge. it means that we haven't such an element, but we have the number of such expressions eta when h. So we have such a set of random values, and one can check that these are Gaussian family of random values. So it is a Gaussian. Namely, it means that we take any finite number of such values, they will organize Gaussian vector. And it is interesting to check the covariance. Because of this expression, maybe everybody understands that this one, expectation of h eta will be equal to 0. But what about covariance? So let us find the expectation of h1 eta h2 eta. To do this, I will suppose that these vectors h1 and h2 have the following representation in the coordinate form. Then, for these random values, we have another representations, which we already discussed. H1 eta is equal to something from n equal 1 to 50 alpha n eta n. H1, H2 eta is equal to some from n equal 1 to 80 beta n eta n. And now we want to have the expression of expectation h1 eta h2 eta. What it will be? When we will have the product of two these sums, we know that these sums converge to the square mean. These etas are independent under different indices. So what will remain after we take expectation? When indices, when we will consider such a product, expectation of alpha n, beta n, eta n, eta n, when m is not equal to n, it is 0 because these two random variables are independent. These two random variables are independent. But when we consider such product, when indices are the same, here is eta, then it will be equal alpha n beta n, because of eta is a standard normal variable. It has variance equal to 1. So one can check finally that it is equal h1, h2. So we have a good family of Gaussian random variables indexed by the elements of Hilbert space and having nice covariance, identity covariance. Actually, we substitute standard normal vector by this family of random groups. And it is so useful that it has its own name. Let us define it. So we will say that this family H eta with the properties which we mentioned is a Gaussian white noise in the space. And now what we are going to do, we are going to express everything in terms of some white noise in the Hilbert space. To do this, I prefer to start from some function of white noise, because our strategy will be formed. We will have white noise, then we will express our random fields, our psi of u belong to G in terms of white noise. Then we will express the local time delta y0 from psi of u in terms of again of white noise. So from this program, one can understand that maybe we can start from taking here usual function, not generalized, then try to go to the limit and understand what happened. So let's try to do this. I will suppose that now we have a scalar case. So one dimensional case. And I am considering f which is acting from R to R and is measured and I am going to consider a random variable of the such kind h eta. So what we are doing, we consider non-linear functionals from our white noise. And this is maybe a simplest one. Just take the value on the one vector from our space. And then taken from this value h eta non-linear function. And I want to have some expression. What it will be in terms of this vector h, this white noise. In order to make our consideration simple, I want to have special vector h. So I will suppose that h has a unit mass. The norm of h is equal to 1. Why I do this? Because in this case I know that this random variable h eta has not only normal distribution, but standard. It has a standard normal distribution. It happens because we know that all these waves has zero expectation, but also we know that variance of this random variable is equal to the norm of H. You remember we discussed covariance, and now taking expectation of the square, we must calculate H multiply on H. And this is equal to 1 by our hypothesis. So we have here standard. Why I'm saying that this will simplify our calculations? Because in this case, one can have an interesting expressions for quadratic functions from standard Gaussian waves. To do this, let me introduce you Hermite polynomials. Hermite polynomials. Let us define Hn of x by the following rule. It is Ex squared multiplying on d over dx and the derivative of the function e minus x squared over 2 and multiplied by minus minus 1 to the power. One can easily calculate the first Hermite polynomials. Is equal to 1, H2, H1 is equal to x, H2 of x is equal to x squared minus 1. Moreover, one can have, and it will be useful for us, one can have a recurrent formula for Hn. So Hn plus 1 of x will be equal x multiplied by Hn of x minus n Hn minus 1. So one thing, such expression, and you see, this expression is very familiar to people who study some orthogonal families of polynomials, because this expression is taken into account 3 subsequent polynomials, n minus 1, n plus 1. And it occurs that really our polynomials are orthogonal with respect to standard Gaussian distribution. Namely, we have the following formula. It occurs that expectation of Hn from our H theta multiplied by Hn from our H theta is equal to delta nm multiplied by the m factorial. Here, delta nm is a symbol of Kronecker. So delta nm is equal 1 if n equal to m and 0 if n not equal to m. So we see that hn are orthogonal. This can be checked using the expression and integration by part formula very easy. Please do it by yourself. But a more important fact is that the system of Hermite polynomials is complete in L2 space with respect to standard Gaussian variable. Namely, we have the following fact. We have the following. That if our function f is such that expectation of f from h eta squared is less than infinity, then it can be expressed as follows. F of h of eta will be equal to the sum from n equal 0 to infinity. Here we have some coefficient an, hn of h eta, where an is equal to 1 over n factorial expectation of f of h eta multiplied by hn of h eta. So this is the theorem, and we have such a nice property of Hermite polynomials. Any nonlinear functional from standard Gaussian random variable can be expressed as the sum of Hermite polynomials from this random variable. Moreover, this sum contains orthogonal in square mean summands, and the coefficients can be found as usual Fourier coefficients of some element with respect to orthogonal system. Here is the expression of the coefficients. I will not give you a proof of this theorem because it lies not in the direction of our consideration. For us, this theorem is interesting because it gives us the way how to express any functional from any nonlinear functional from our white noise. Now we can go further. We can go further and try to consider case of more complicated functionals. Namely, I will take here what we are interested in. I will take here delta function. Yes. So we have such an expression. What I want to do, I want to consider delta function at some point y. Let me recall it. Consider one-dimensional case. So we have more vectors. Delta in point y of the same random variable h eta. what it will be? One can say, we don't know what is delta from the any random variable. So why we have to obtain some good expression? For example, if this series conversion square, we will get some random variable. Yeah? But what is this? And here, situation is exactly the same as we have today in the beginning of the lecture. You remember, we have at least h, and we have no eta, but there exists h eta for any random. Yes. So more or less the same happened here. For example, let us discuss formally what can be expectation of delta function from some good random variable. So this is our aim, but now I just take psi to be a random variable. Is a random variable. Such that it has density. It has density, continuous and bounded density. I will denote this density by P. Then, let me recall you a standard formula from the first lecture on probability. Expectation of some function f of psi is equal under such assumption to integral f of x, p of x, dx. This is a standard formula. But since we have such a good density, now one can calculate expectation of delta y of psi. What is? Let us define this expectation as follows. It will be the integral delta function y x px dx, and by the definition of delta function, it's equal to p of y. So you see what happened? We have not such a random variable, but its expectation is well defined. Moreover, suppose that we have another one, function g, such that the product g by p again is continuous and bounded on R. Then what one can say? Then one can again define this expectation given such product. What it will be? It will be again the integral over R. Here is delta function concentrated at the point y. X. Here is p of x, j of x, dx. And it is equal, again, we have this product and apply delta function to this product. And we will have finally p y, j y. So one can not only calculate the expectation of this random variable, say in brackets random variable, but also expectation of its products with different random variables. And this is exactly our case. We can calculate the following expectations. For any n which is greater or equal than 0, one can calculate the following expression. Expectation of delta y h theta multiplies Hermite polynomial hn h theta. Why I am sure that we can do this? Because this is a standard random Gaussian random variable. So it has density, which we already very well know, e in minus x squared divided by 2. Yeah, this is a polynomial. So product is for sure continuous and bound. So one can check that now our formula book, and what we will have? We will have 1 over 2 pi square root. This is a value of the density at that point y. Yes, multiply on the hn at the point y. Here is the answer. We know what is this expectation. From this point of view, we can go fast. And now we can have at least formal expression for the series for our delta function. Now, using this expression for the coefficients, we can go further and get the following expression. The delta function at the point y on random variable h theta is equal to the infinite sum from n equals 0 to infinity 1 over n factorial. Here we have e minus y squared divided by square root of 2 pi multiplied by h and y multiplied by h and here multiplied by h and of h. So as the end of our lecture today, we have such a formal expression for delta function from the Gaussian random variable. Of course, we have to understand that this series does not converge the square root. This is not a usual random variable, but it will be interesting that when we will discuss local time, we will consider integrals from such random variables. So we will get integrals here. And it occurs that in some cases, such obtained series converge. And we will get the expression for the local time. This is our goal for the next lecture. Today, we did our work. Thank you for your attention. If somebody has questions, please. Okay.